In this video, I'm just going to be going through all the 3 problems in this contest and how I'd solve them in the span of around 3.5 hours. So, problem 1, flight routes. Bessie has discovered that her favorite pop artist, Elsie Swift, is performing in her new Eras tour. So this is obviously a reference to Taylor Swift's Eras tour that happened last year in 2023. Unfortunately, tickets are selling out fast, so Bessie is thinking of flying to another city to attend the concert. So there's a total of N cities, where N is at most 750. They're labeled from 1 to N. For every single pair of cities, there exists either a direct flight from the lower numbered city to the higher numbered city, or there does not exist a direct flight. So in total, there's n times n plus 1 over 2 possible flights. For this example, let's say there's 5 cities, then these are the possible direct flights that could occur. So there's 10 possible direct flights. All of them might exist or they might not exist. We define a flight route from city A to city B, where A is less than B, as a sequence of K is at least 2 cities from A to B, such that it's in increasing order, such that for every single city, there is a direct flight from the current city to the next city. So from 1 through N, there might be a flight route that looks like this. There can be as many cities as we want in the middle, but each city just has to be connected to the next by a direct flight, and that is called a flight route. So the information we are given is for every single pair of cities A and B, we know the parity of the number of flight routes from A to B. So it doesn't just have to be from A to N. We could go, for instance, from, let's say, 2 to 8. And then we don't know how many flight routes there are from 2 to 8. So these could be a few examples, but we know the parity. So whether there's an odd number or an even number of flight routes. So the question we're asked is, what is the total number of direct flights between all pairs of cities, only given the parity of the number of flight routes between every pair? Since we're given that n is at most 750, doing this in O(n) cubed time should work out okay, because let's see here, 750 cubed, 4 times 10 to the 8. And obviously we're going to have some constant factors to cut this down, because we won't need to check n cubed possible things. We'll divide by 2s and 4s somewhere, but O(n) cubed is what we're going to be aiming for. So here's the idea. We're essentially going to be filling out a dynamic programming table, and this table is going to tell us whether there exists a direct flight from city I to city J. So again, the data that we're given is the parity of the number of flight routes between city I and city J for every single pair of cities I and J. So this 0 over here tells us that the number of flight routes between city 2 and city 4, that is an even number of flight routes. There are a total of only 2 possible flight routes. Either you go from 2 to 3 to 4, or you go directly from 2 to 4, depending on what is available, but there's an even number. So here's what we're going to do. We're going to fill out this table, which is an n by n table telling us between city I and city J for every single pair of cities whether there exists a direct flight from I to J. We don't know this table at the beginning. It's our job to figure it out, and we're going to start with the cases where I and J are separated by just 1 unit. So the cases where I is directly behind J. Once we have that information, we're then going to fill out the cases where city I is 2 spaces behind city J, and we're going to use the information that we already computed to figure out those numbers. So again, the really easy ones are cases where I and J are consecutive. So we're going to start with I equals 1, J equals 2. This information is really easy to find because we can just look it up in this table. We know that from city 1 to city 2, there are an odd number of flight routes, but there's only one possible flight route, which is going directly from city 1 to city 2, since there's nothing in between. Since there's an odd number, we know it must be 1, because there either is no flight route from 1 to 2, or there is a flight route. Again, there's only one choice. So we are given that it's an odd number of flight routes, which means that there must be a direct flight. Similarly, from city 2 to city 3, there must be a direct flight, because otherwise we would have 0, which is an even number. From city 3 to city 4, there's an even number of flight routes, and since there can only be 0 or 1 flight routes, there must be 0, because that's the only even number, meaning there is no direct flight from 3 to 4. And then we fill this out again for 4 to 5, there's an odd number of flight routes, which means there is 1 direct flight. Okay, so that was a base case. That was the case where I plus 1 equals J, meaning they're consecutive. The next case is I plus 2 equals J, so they're separated by 1 city in between. For example, from 1 to 3, let's look at whether there exists a direct flight here. To figure this out, it's pretty simple, because we know there is a direct flight from 1 to 2, and there is a direct flight from 2 to 3 based on the information we computed in the last stage. Meaning, this gives us 1 flight route from 1 to 3 already, and since there's only one other possibility, which is going from 1 to 3 via via direct flight. We don't know if it exists, but looking at this table over here, we know from 1 to 3, there are an odd number of flight routes, meaning there cannot be a direct flight from 1 to 3, because if there were, then there would be 2 total ways to get from 1 to 3, which is an even number, meaning there does not exist a direct flight from 1 to 3. Now we consider city 2 to city 4. We are given that there are an even number of flight routes from 2 to 4, and we know there is a direct flight from 2 to 3, but no direct flight from 3 to 4. Does there exist a direct flight from 2 to 4? The answer is no, because there are already 0 ways to get from 2 to 4. If we did have a direct flight, that would be 1 total way to get from 2 to 4, but since we know that it's an even number of ways, this cannot be the case. Therefore, there are 0 direct flights from 2 to 4. Now, finally, we look at 3 to 5 for this stage. We know that there is no flight from 3 to 4, but there is a flight from 4 to 5. And this time there are an odd number of ways to get from 3 to 5. So the question, does this direct flight exist? The answer is yes, because we need it in order for the total to be 1, since it's an odd number. If we didn't have this direct flight, there would be no ways to get from 3 to 5. So the answer to this must be 1. There is a direct flight from 3 to 5. The next step then is to consider I plus 3 equals j, meaning our cities are now separated by 3 steps. So let's look at 1 to 4. We're going to do casework since we're flying from 1 to 4 on the last city that we visit before we hit city 4. So we could either go from 1 something something to 2 and then to 4, or we could do 1 something something 3 and then to 4, or 1 directly to 4. So again, there's 3 cases based on what is the last city that we visit. For the first case, we're going from city 1 to city 2 and then to city 4. We need to know how many ways there are to do that, or rather the parity of the number of ways to do that. Since there is no actual direct flight from 2 to 4, this is impossible, because we're saying we want our last city before city 4 to be 2, but there's no way to get to 4 from 2 directly, so this is impossible. The next case is going from 1 to 3 and then to 4. There is also no direct flight from 3 to 4, so this is impossible. But we know that from 1 to 4 there are an odd number of flight routes, meaning these can't be the only ways. In fact, there's no ways to do that. So there must be a way to get from 1 to 4 directly, meaning there's a direct flight from 1 to 4. And now we can do 2 to 5. Again, there's 3 possibilities. We can either go from 2 to 3 and then directly to 5, or 2 to 4 and then directly to 5, or 2 directly to 5 straight away. 2 to 3 and then to 5. So 3 to 5, there is a direct flight from 3 to 5, which is good, meaning we need to check the parity of the number of ways to get from 2 to 3. And looking it up in this given table over here, it's odd. So we know there's an odd number of ways for this case to go from 2 to 3 and then directly to 5. So the second case, going from 2 to 4 and then directly to 5, there is a direct flight from 4 to 5, so that's also good. And from 2 to 4, there are an even number of ways to get from 2 to 4 directly or indirectly. So this is going to be even. Now, if we add this up, so far, odd plus even means there's an odd number of ways to get from 2 to 5. Is that the case? Yes, that is the case according to the given information. So this means there cannot be a direct flight from 2 to 5, because if there were, that would mess up the parity, meaning there would be an even number of ways. But we know there's an odd number of ways to get from 2 to 5, so there's exactly 0 ways to get from 2 to 5 directly, meaning this number is 0. So now we're done with the I plus 3 equals j case. Finally, we have the I plus 4 equals j case. There's only one flight that has a gap of 4, and that's from 1 to 5. So we're going to have 4 cases here. Either we go from 1 to 2 and then directly to 5, or 1 to 3 and then directly to 5, or 1 to 4 and then directly to 5. I just realized I've been writing behind my head this whole time, so I'll be zooming out a little bit so you can see better. So 1 to 2 and then directly to 5. Let's see, 2 to 5, there is no direct flight path, so this is an even number. 3 to 5, there is a direct flight path, so let's check the number of ways to get from 1 to 3. That's an odd number, so there's an odd number of flight routes from 1 to 5 in this pattern. Third case, 1 to 4 and then directly to 5. Let's see, there is a direct flight from 4 to 5. So the number of ways to get from 1 to 4 is an odd number, meaning this is also odd. So if we add up what we have so far, we get an even number of ways to get from 1 to 5. Now, is that the case? Let's see. No, it's an odd number, meaning we need a direct flight from 1 to 5 to make up for the fact that so far we only have an even number of ways to get from 1 to 5, but there's actually an odd number. So this should be a 1. Now, if we look at the explanation, there are direct flights from 1 to 2, 1 to 4, 1 to 5. And that is indeed what we have here, 1 to 2, 1 to 4. And that is indeed what we have here. We have 1 to 2, 1 to 4, and 1 to 5. I'm going to just going to erase all of this really quickly. And then we also have flights from 2 to 3, 3 to 5, and 4 to 5. So 2 to 3, 3 to 4, and 3 to 5, which is exactly what we have in this table. And then we also have flights from 2 to 3, 3 to 5, and 4 to 5, which, as we can see, is exactly what we have in our little table over here. So to summarize, our strategy is roughly like this. Step 1 is to initialize an empty 2D array DP for dynamic programming. It is a 1 in the ith row and the jth column if there exists a direct flight from I to j, 0 otherwise. We're going to fill in this DP table incrementally. We're going to fill in the base case, which is I plus 1 equals j. So for consecutive cities, we know there's a direct flight if the parity of the number of flight routes between those two cities is odd, because they're consecutive, so there's only one possible flight route, which is the direct flight path. For the general case, if I and j are more than one city apart, then we're going to consider the possible ways that we can get from I to j so far, not including the direct flights. So we're going to consider all possible cities in between k, for I is less than k is less than j, where k is the last city that we visit before we take a direct flight to j. We can use a for loop for this. So for every single city k, this is only possible if there is a direct flight from k to j, which we know, based on this table, we should have filled it in already because we go from the smallest gaps to the largest gaps, and the gap from k to j has already been filled in. So we know whether there exists a direct flight from k to j or not. If there does, then we look at the parity of the number of ways to get from I to k, and this is given in the table from the input directly. So if there's a direct flight from k to j, we know the parity of the number of ways to get from I to k and then to j. Once we do this for all k, we can add up the numbers and find out the parity of the number of ways to get from I to k via flight route so far. If that matches the given parity of the number of flight routes from I to j, then we're all good. Otherwise, it doesn't match, which means we missed one flight route, which is the direct flight from I to j. So we check those parities. If they match, all good to go. If not, then we need to add a direct flight from I to j, and we mark that in the DP table. In the end, we just add up all the ones in the DP table. We're going to have ones or zeros based on whether there's a direct flight or not. If we just add all of those up, we're going to get the total number of direct flights. For time complexity, let's take a look. We're going to loop through n squared possible pairs of cities to find out whether there is a direct flight between them. For every single pair, we're going to need to look at all of the cities in between to add up the number of flight routes that we already have to determine if the parity matches or not. So for every single pair, n squared, we're going to do an additional n in between. It might be less than n, which is good because that reduces the total number of cases that we need to check. So n squared times n is on cubed. That's going to be our total time complexity, which, as stated earlier, is probably going to be fast enough for n equals 750. I did try this with Python first, but that was too slow, so I had to use C++. So let's take a look at the code. We initialize our parity array to store the input information. This is basically just reading the entire input, but that's just details. If you want to check out the code, the link to the GitHub repository will be in the description. So we store that inside an integer array, which is implemented as a vector of vectors. We're going to call it parity. So parity ij is going to be the parity of the number of flight routes from I to j. That's the information we're given. Next, we're going to loop through every single pair of cities, and we're going to do this in increasing order of gap size. So to do this, I'm starting I at n-1, which is the very last city, and then looping backwards. And then I'm going to start j at I plus 1 and going to n. So we're going to start from the end and go backwards for I. And as we do that, j is going to start at the closest one to I and then loop forwards. This looping order is a little bit different from what I described in the first section, but it works out to be all right because all we need for determining if there's a direct flight between I to j is to have all the information for k to j for all k between I and j, and that will have been computed already according to the order of our for loop. So we don't need to worry about that. For every single pair of cities I and j, then we need to count the parity of the number of ways to get from I to j so far, without considering the direct flight from I to j, to see if the parity matches up with the parity we're given. If it doesn't, again, we're going to add that direct flight from I to j. So we're going to keep a count of the total number of ways to get from I and then to some city in between and then directly to j. Inside this for loop, that's what we're doing. We're taking the parity of the number of ways to get from I to k, but only adding that if there is a direct flight from k to j. If there is not, this value is going to be 0, which is going to nullify the effect of this. If there is a direct flight from k to j, again, this is going to be either 1 or 0, and we're going to add that to count. At the end, if the count matches the given parity of the number of flight routes from I to J, then we're good. If not, though, then we're going to add a direct flight from I to J and increment our answer by 1. So yeah, that's it for problem 1. I think the trickiest part of this problem for me was I first implemented it in Python with an O(n) cubed algorithm like this one, and it was too slow because 750 cubed is 4 times 10 to the 8. So for Python, that would have been too slow. So I moved on to problem 2 and problem 3. But then I revisited this problem, and I was like, why don't I try implementing it in C++? Maybe that'll work. I didn't think it'd work because 750 cubes still seemed too big, but then I did it, and it was just fast enough because C++ is just that fast. So the moral of the story, I guess, is if you think the time complexity of your solution is too slow, don't give up just yet. You might just need to implement in a different language. So for example, C++ if you were using Python, or if you haven't implemented it yet, just implement it and see if it works. But this video is getting a little bit long, so I'm going to post problems 2 and 3 separately. Stay tuned for those, and thanks for watching.